Good morning. I'm Jason Hartline from Northwestern University, and I'm really delighted to be at the Google Market Algorithms Workshop presenting joint work with Northwestern students Modibo Kemara and Alec Johnson, Mechanisms for a No-Regret Agent Beyond the Common Prior. This paper appeared last year in Vox, and you can find the manuscript on arXiv. So to give you some motivation for the context of this paper, uh, it comes from online markets. There's lots of data in online marketplaces, and a principal designing such a marketplace that has lots of data could potentially publish views on this data for the participants of the marketplace so that those participants be more informed and potentially can um, uh, get better outcomes in the marketplace. And the principal can also steer the participants towards getting outcomes the principal desires. This was the topic of a paper from a few years back that I presented in a previous market algorithms workshop at Google uh, by with some co-authors. And so the point of this paper, though, is revisiting this situation where there's a lot of data and the principal potentially can reveal some data to an agent and ask the question of, well, what happens if the principal is learning about the environment at the same time as the agent is learning about the environment? So this plugs into a very important and interesting agenda in game theory, which is, can we replace equilibrium with prior knowledge with models of learning? And there's been almost 2 decades now of work making this connection, showing that learning agents are related to standard equilibrium concepts like correlated equilibrium. And then looking at analyses we might do typically of agents in equilibrium, and we're going to then apply those analyses to learning agents instead. So in particular, looking at the price of anarchy for learning agents, or attempting to do econometrics for learning agents, and more recently doing mechanism design with learning agents. In comparison to these papers, the paper I'm presenting today is going to be about designing learning mechanisms for learning agents. Great. So a sort of canonical framework for mechanism design is what's called common prior mechanism design. And that views a mechanism design problem as a Stackelberg game of incomplete information and includes settings like contract design, Bayesian persuasion, and delegation, where there's a principal deciding on a policy, an agent responding by taking some action, and nature selecting some hidden state that affects the payoffs of both the principal and the agent. These models for a principal to adopt a good policy and the agent to understand and respond to this policy typically require common prior belief on both parties, the principal and the agent, about this state that nature is choosing. For example, in this scenario I've illustrated here, maybe there's a 40% chance that the policeman is at the donut shop. So the goal of this paper is to replace this common prior assumption of the principal and the agent with adversarial online learning. And what that means is we're not going to make any assumptions on the sequence of states offered by nature, and we're hoping that a principal and agent can together learn how to interact. We're going to be taking the perspective of the principal and looking for mechanisms with low policy regret. And this is sort of kind coming from this perspective that we have in market design, that the principal has some form of commitment power, um, and they're going to want to wield that commitment power to publish a mechanism and not be sort of pressured off of this mechanism by potentially bizarre behavior of the agent. Okay, so the principal is going to commit to a mechanism. The principal is able to learn nature state. The agent, on the other hand, is going to learn from both the principal's policy and nature state, and attempt to achieve good payoff in this world. The principal, we're going to be looking for policy regret versus hindsight regret, like we typically might look at in online learning, because decisions the principal makes at the beginning might affect the agent's learning algorithm, and therefore the principal really has a policy regret problem, because we don't want to just measure our principal looking back in hindsight on policies they could have chosen, assuming the agent is going to use the same actions. But these actions of this policy of the principal might impact the agent's action since the agent is learning, um, and therefore we would like sort of a policy regret bound, saying if the agent had run a different policy and the agent had responded to that different policy, does the principal have low regret compared to that? So a key thing that comes up in this agenda that we have is understanding how to control the agent's behavior when the agent might potentially have extra information that maybe the principal is not aware of. And to give you an illustration of this, consider a tortoise given the challenge of walking 1 kilometer. And it's probably a stretch to imagine this tortoise can get 1 kilometer in an hour. Imagine this like an uninformed agent satisfies a no regret guarantee. On the other hand, we might have a hare also attempting to travel 1 kilometer. And if we give them a constraint of doing this in 1 hour, well, they don't feel so constrained. They can actually take a lot of detours, and what that means is that their behavior is going to be less well controlled by this constraint. Okay, and so just requiring an informed agent to satisfy no regret might be too weak an assumption, because maybe they can satisfy no regret because of their extra information quite easily, and then do all kinds of other things that maybe we'd be concerned about them doing. So what we'd really like to do is, if the informed agent has extra information, we'd like them to satisfy no regret conditioned on that extra information. In other words, we'd like to move the goalposts to be appropriate for the information that the agent has, so that we can put a constraint on their behavior that's appropriate for their abilities, so we can be sure that they're not doing things that we would be unhappy about them doing. Great. So the typical approach in this literature on no regret learning tries to put bounds on the agent's behavior, for instance, in the form of a no regret constraint. In hindsight, the agent prefers her algorithm to any fixed action. And as we just saw, this might not be a great constraint if the agent has information. So it's going to be insufficient because, and even if we're not worried about the agent actually having information, because we're looking at adversarial machine learning, if the adversary correlates the state with the agent's action, then it looks like the agent has information, and this then means we haven't constrained the agent like we'd want. And so the key idea that we're going to use is that the agent's behavior reveals any information that they might have. And So we're going to look at calibration, otherwise known as internal regret, and require that an agent has no regret with their past behavior as context. If they had any information in this that was relevant to the payoffs, it needs to be, if it helps them, it must be revealed in their past behavior. And so if we require no regret with past behavior as context, then uh, then we know they're using the information that they have. Unfortunately, this is also insufficient to admit low policy regret mechanisms. Um, and the idea is the adversary can condition the correlation between states and actions on the principal's policy. And so if the principal chooses one thing, maybe the agent is informed, and if the principal chooses something else, the agent is uninformed. And this this means we're going to be unable to get adversarial guarantees about learning with a learning agent. So our approach to this is to introduce a notion which we call counterfactual calibration. And the idea is, let's use the information that's revealed by the agent's both on-path and off-path behavior. Okay, so on path, we're talking about the agent's behavior under the principal's mechanism, and let's also look at the behavior that the information they would potentially reveal off path on other policies the designer could choose. Okay, and so counterfactual calibration says that the agent has no regret with the behavior that they would make on and off path as context. Okay, and really what this definition is getting around is that the agent must fully and consistently exploit any revealed information they have, and they can't sort of sometimes exploit it and sometimes not exploit it, depending on actions the principal may make. Okay, so here is an illustration. So I'm going to imagine, a typical setting of contract design. There's an easy task or a hard task. That's the state. And the agent's action is either to shirk or to work. So let's suppose that under our mechanism, the agent chooses to always work. That's great. And the tasks are alternating between easy and hard. But if we took some other counterfactual policy, maybe the agent switches off between shirking and working on the shirking on the hard tasks, working on the easy tasks. So the idea behind counterfactual regret is that the agent has to have no regret where the context is given by this mixture of actions that they take across the different policies of the principal. Okay, so this context is given by this last line below, and we'd like the agent's behavior to be calibrated with respect to this this context. Cool. So with that main sort of conceptual definition under our belts, let's look at our first result. So our first result is look at an uninformed agent. And our goal here is to reduce the online problem to a robust version of the common prior problem. So here's the robust version of the common prior problem we look at. Okay, so we're going to be looking at a misoptimization robust policy for a common prior. And a misoptimization robust policy for common prior is a policy of the principal that's good as long as the agent makes any approximately optimal strategy. Okay, so this is sort of a min-max, a max-min optimality criteria for the principal that says the principal maximizes their payoff when the agent chooses a approximately good strategy that minimizes the principal's payoff. Okay, and then the theorem is the following. Let's assume the agent is consistent and not more informed than the principal, and we can get these two. We can enforce this by assuming that the agent is counterfactually calibrated and also achieves non-negative regret. Okay, so their regret is non-negative, uh, which is saying that whatever information they have is not giving them anything because they have non-negative regret. And they're counterfactually calibrated, so they always use whatever information they have. And then our mechanism is the misoptimization robust policy using a calibrated forecast as the prior. And for this mechanism, the principal's policy regret vanishes. Cool. Just to dive in a little bit deeper, what is a calibrated forecast? Well, this is something that the principal can learn using a no internal regret learning algorithm to try to learn what the prior distribution of this state is with a cost given by a proper scoring rule. Okay, so this is a way to come up with a calibrated forecast of nature's state. Our second result is for informed agents. Again, we're going to be reducing our online problem to a robust version of the common prior problem. And we're going to borrow a notion from Bergman and Morris, which is a information robust policy for a common prior. And that is a policy that's good under any additional information that the agent might have. Again, it's a max min and condition. We want to maximize the principal's payoff for the worst case information that the agent might have. Okay, so we're going to assume that the agent is counterfactually calibrated, which means they consistently exploit their information. And then we're going to use a misoptimization and information robust policy for a calibrated forecast. And the result is the principal's policy regret is at most the cost of information robustness. Great. Thank you for listening. To wrap up what we've done today, we're replacing the common prior with online learning. For a rich class of single agent mecha design problems, we're able to show that this counterfactual calibration idea can approximate non-Bayesian rationality. And this idea was that if the agent's behavior reveals useful information in one path, she must also exploit this information on other paths. There are a number of open questions. One is looking at bandit feedback. Another is looking at mechanisms that may be able to adapt to information that the agent reveals that it has. And the final open question is, more explicitly exploring computational tractability issues that arise in questions like these. Again, the paper you can find on arXiv, and thank you very much.